For 6 intense weeks during the summer of 2013, 37 pre-freshman students from Morehouse, Clark Atlanta University, and a local high school participated in the Harp program. Nothing has such power to broaden the mind as the ability to investigate systematically and truly all that comes under thy observation in life.
My name is Dr. Lycurgus Muldrow. I'm the Director of Sponsored Research and Integrative Activities for the Division of Science and Mathematics at Morehouse College. HARP stands for High Altitude Research Project. It's a term that was developed by a number of institutions that have created a team of undergraduate schools, mostly in engineering, learning how to do high altitude research balloon launching. We have a program called the Pre-Freshman Bridge Summer Science Program. And this pre-freshman Bridge Summer Science Program is for pre-freshmen that are interested in going to college at Spelman, Clark Atlanta University, but specifically at Morehouse College. So we can take this and incorporate this into our summer program where the students actually send research projects to the edge of space and back and recover them. And I'm always looking for exciting new projects in this pre-freshman Bridge Summer Science Program that will inspire the students to go to the next level. And when that opportunity came, I knew we had to do it.
Welcome to the laboratory component, the HARP, which stands for High Altitude
On June
Research.
10, 2013, the Morehouse STEM program commenced for the 7th year. 37 pre-freshman students from Morehouse, Clark Atlanta University, and a local high school
number one,
began
two,
their
or
HARP
three
experience.
lab that you like to go into, and then we're going to match you up based on your number one preference, number two preference, or three preference, and your major. For example, if you're majoring in mechanical engineering, it makes sense that you should, for example, be on the launch, recovery, and design team that's designing the craft. Or if you're majoring in computer sciences, it may make sense for you to be in one of the robotics teams that has to program these robots to do specific things in this launch, okay?
So these are the 5 basic groups of research that's going to be involved. However, none of this can take place unless we have a balloon launch. And so we've got a design, launch,
and recovery team, but we also have responsibility for designing the payload and then tracking that balloon as it launches and then doing the recovery. Besides mentoring this group, I also act as sort of a coordinator for the other research groups so we can bring all of the research experiments together to go onto the payload that's launched into the atmosphere.
My name is Dr. Juana Mendenhall. I am an assistant professor at Morehouse College in the Department of Chemistry, and I'm with the biomaterials team. Can mean like biological, right? Something like of the body, or something that can be biocompatible for the body so it won't kill anybody, right? And a material is simply something that can be man-made, something that's synthetic. We can actually make it in the lab. What we do in the biomaterials lab is that we actually fabricate biomaterials that can be used as scaffolds or tissue scaffolds in someone's body. So the use of actually taking our materials up in a weather balloon will allow us to see what would happen to materials if they were implanted in someone's body. So what the students have actually done in our lab is actually started implementing therapeutic agents into the materials to see if they can actually help control degradation process and hopefully have a healthy effect on tissue regenerating at higher altitudes. The HARP balloon is going what? It's going constantly up in the atmosphere. As it goes up, it's depleting out the oxygen levels that are essentially down here on Earth, right? So as it starts going up, we want to study how that depleted oxygen level, or that level of oxygen, actually affects our materials. Now, if we can figure out how our materials are affected at that high altitude, we can do what? We can alter it using some chemistry, change the materials we make to make them more optimal, so as they go up in the altitude, that they will actually capture those unwanted molecules that are in the air, and they'll essentially heal somebody's body if they're going up in space or if they have a disease state in their body. Okay?
What we're doing this summer is working with this program to help some of you learn how to shoot video, how to edit video. You'll also be documenting your fellow HARP student participants as they go about developing their aspects and components of this project.
So my name is Darkale Reuben. I'm a postdoc at Clark Atlanta University in the physics department, and I am a facilitator for the battery team, so a lithium-air battery team.
I'm Dwayne Jackson, professor of psychology now. I am the team leader for the termites who are going up in space, which we're very excited about.
I'm Mihiru Shashikala Hewa Bostantirige.
I'm Indra Sapkota. We are energy group, so we have to generate energy from sustainable source. So.
I'm Ms. Thomas. I will be doing the robotics class. I am a PhD candidate at CAU in computer science, system science / computer science.
The robotics aid the biomaterials lab by constructing a mechanical arm that opens up the petri dish at a certain altitude and have it open for a certain time frame and then close it. Also the robotics aid the graphene lab where we have 3 different vials that they have materials in, and the robot was created to rotate between those 3 different vials, opening them up at certain time intervals and then close them.
Now the students get out of working with me really how to be a scientist. They learn how you deal with proposing a question or a purpose, forming a hypothesis, and then actually doing the research, knowing that you're going to have a lot of blind alleys and you're going to have more failures than success.
They come up with the design themselves, they come up with the programming, and so this is really a hands-on guided inquiry lab where the students take charge and they develop their robots on their own.
And these are students that have declared a STEM major. STEM stands for Science, Technology, Engineering, and Mathematics. We've been doing the program, this is our 7th year. And the emphasis on this program is scientific literacy. The idea is real simple. 17% of the United States population is not scientifically literate. They don't understand how research happens. They don't understand how science happens. And because of that, they really have a disconnect between science. The reality of it is incoming freshmen that say they want to major in science are not scientifically literate. So if we could show them the big picture of science, have them do a little research, have them do a little science, the literature shows that they may become more excited about science and then stay in science. And it's a dismal national outlook on science and STEM simply because 40% of African American students that start a major in STEM don't finish it. So this pre-freshman bridge summer science program, which we've been doing for 7 years and tracking the data, has shown that the students do much, much better in their courses and they stay in the major. In fact, 15 to 20% better than the average other STEM students that didn't participate in the summer program.
The Recover team was composed of 6 students, given the responsibility of mastering the Stratostar kit, which included learning how to launch the balloon and recover the craft containing the research payloads. This team was also responsible for designing the payload craft that would carry the 5 research projects into near-space conditions. The payload craft was creatively designed with specific size specifications with a specific weight load requirement under 12 pounds.
Our little container, that's our balloon launch system.
We do what is called an engineering design process, where we are trying to realize what the problems are from the other research groups and how we can accommodate them and get all of their research programs situated in a containment vessel that will go up with the balloon, and it has to be able to survive coming down with a parachute. So it's not going to be a gentle ride coming down, so we've got to design for that.
My name is Dakari Franklin, and I'm with the design and launch team. This is the pool noodle. It was longer like a regular pool noodle, and we've been cutting this and using this as the cushion for the fall.
And then the students get to build this payload section. The other thing is that they have to learn how to use a GPS device to track. They have to learn how to read a regulation, a federal regulation that governs the launch of these balloons.
What this does is it transmits to the command module, which is now outside, and we're trying to get it to, it's actually sending back a signal to me over here on the antenna. But what it doesn't send me yet is the GPS coordinates. It takes a while for it to pick up GPS coordinates. Every time it moves somewhere, it then has to figure out all the various satellites. essentially built in to receive from the satellite. And GPS satellites never receive data from it. They just send data out, and you capture it on your device and then use it.
How much do you?
They have to learn how to deal with simple mathematics to predict where that balloon might go with the winds that are prevailing that day.
You got 33 degrees, and that's in degrees. Okay.
33 divided, take 7, 4, 8, 9, 7.
No, you got 0.7, isn't it?
We're trying to launch a flight that doesn't require us to get permission from the federal government. So we have to fall within certain limitations. And the first limitation is can't weigh over 12 pounds. You can't obviously launch in a airspace, controlled airspace, such as around an airport. You can't launch if over 50% of the cloud cover. And you have to have a visibility of 5 miles. The problem that we have really to deal with is the weight restriction. The weight restriction requires a limit of 12 pounds, not counting the balloon, but everything else, the parachute, the instrumentation, and all of the experiments that the students produce, all has to fall into that 12. Yeah. Guys, there is something going on. I don't know what. Neither one of them is working, so we do have a problem. Be careful about pulling on the antenna. It might be better to push. Yeah, you did. Yeah. Go ahead and take that. Yeah. You always need a light skin in the picture. Because we interact with all of the other teams, the research teams, we have to become aware of what their requirements are and what the purpose of their research is, so we can design our module to accommodate their needs. So my team has a liaison for each of the other research teams. But what I want them to do is to hook it up with their solar cells and see if it heats up.
Well, what they said they were going to do is their solar cells are recharging a battery, and they'd hook this up to that battery.
My name is Caleb Bugg, and I'm part of the Sustainable Energy team here doing the Harp project at HBCU Up Camp. Right now, we're trying to maximize the use of our solar panel. So currently we're doing outdoor testing, of course trying to get the maximum amount of energy from the sun. We've Googled that this is a 1 watt resistor, and we're not quite getting that on our readings yet. So we've come up with a couple ideas, such as using tinfoil.
My name is Matthew Mullins. I'm here with Sustainable Energy. And right now we're trying to see if this aluminum foil can help increase the sun's intensity on our solar panel.
Our mentors are teaching us about resistance and things like that, and how voltage and resistance and all these electrical engineering tools combine to make like watts increase, or like the relationships between all of these. So right now we're just finishing up our outdoor test, and we're going to have a lot more tests during the week and during the following weeks, and we just hope that eventually we'll be able to have a foundation for the kids that come after us in this program, so that we can eventually have a sustainable energy source to replace the batteries that are being thrown out every year. The reading now is at about 0.5 watts, and that's at about 2.3 volts. So as I mentioned, it's a 1 watt solar panel, so we want to get it from 0.5 to as close to 1 as possible. The chances that we can get 100% efficiency aren't very high, but to think that we can get into the 0.8 or 0.9 range is very likely. So that's what we're trying to do. So you have to use, like I said, the electrical engineering tools. We're using small resistors, we're using increased sunlight intensity, things like that, and we're trying to maximize the wattage. Wattage is joules per second, so wattage is telling you like your power output in a given amount of time, and that's what you want to increase in order to power something such as the Harp payload.
So the objective of the battery team is for the students to work together, first learn what a battery is, the history of batteries, and what is the latest technology in battery technology. We got our prototype batteries from Acceleratron, a local Atlanta company.
Did we get everybody fitted in all right? I thought maybe we might not have enough chairs. Yeah. So everybody came that you had planned to come? Yeah. But let me first introduce myself. I'm Tony Pace. I'm the Chief Operating Officer for the company here. I'm glad you guys were able to come visit us today. I appreciate you coming by to listen to us and see what we're talking about. During the course of the day today, I'll ask you some questions. We'll talk a little bit about what we're doing here, and hopefully I'll get a chance to find out some of what you guys are doing, and I'll give you a short tour, and then once we're back from the tour, then you'll be able to talk to Dr. Johnson. You can ask him some questions as well about him and his background. So
there was a man named Lonnie Johnson who has become the idol and an icon for current black scientists today. He was an engineer at, I believe it was NASA, where he worked on some of the space shuttles, and he invented the super soaker water gun. And a lot of people know him for that.
I mean, some of the work that we're doing here is very secret work, and most of it is proprietary. So we're cautious about what ends up on film because we don't want our competitors to find out, what we're doing. And so you guys will have to bear with me during the course of the discussions today, particularly the cameraman.
Later, he started his own firm called Acceleratron, and a couple other engineering firms. A long time ago, we sort of got in touch with him because he's in the Atlanta area, and we developed a relationship with him. So every summer, we send students to Acceleratron to do research. We wanted to expand that relationship. And when we knew he developed this air lithium battery, we asked, well, and they have a contract to put one in a blimp, but it's not been sent up to the edge of space. A blimp that goes up and stays for a year. So what happened, we said, well, can we send one of the batteries up, just to test to see how it works, which is a great research project.
The original question is, what's so special about this lithium air battery? Okay, and sorry?
High energy.
Somebody said it has high energy. The question was, how much higher energy does it have, right? Okay. It took the guys at NASA, what was it they said, 10 years to get a 10% improvement on lithium ion batteries, all right? The battery technology that we're working on here has the potential for 10 times the energy of conventional lithium ion batteries. So if you're driving this Toyota Prius, right, and you replace that Toyota Prius battery with our battery, you should be able to go 600 miles on a charge, right? If it's 10 times, yeah? Come in and say that louder so everybody can hear you.
He was creating a heat pump that used water instead of Freon, and he ended up aiming one of the hoses at a tub and it shot water.
So that's how you came up with the idea for the super.
Yeah.
Very good. Okay. One day while Dr. Johnson's in class, there's a professor talking about thermodynamics, right? That particular day he was awake and listening during class and got the idea for the super soaker, okay? So for all the rest of you guys, you have to be careful. You don't want to be asleep in class because a $2 billion idea just might go straight over your head, right?
Welcome to Atlanta, for those of you who have come from afar. Let's see, I guess Tony's probably told you a lot about what we're doing here in terms of the energy technology development. Progress has been made with some of the corrosive issues with lithium air batteries. There are two types of corrosive issues. There's the bad kind and the good kind. Batteries work, the lithium air battery that Tony I'm sure talk to you about, that discharge process is a corrosive process. The lithium is coming over into the air and getting oxidized, and in the process you generate electricity. The bad corrosive type is when you have a defect in the packaging and air or oxygen can get into the battery and react with the lithium without having it discharge or something like that. So the corrosive issue is more of a packaging and making sure it's sealed properly. And for the lithium air battery, actually corrosion is actually the discharge process by which you generate the power. Well, I'm obviously very excited about the work we're doing right now in energy. I learned that lesson very well in the dart guns. Not only did I invent the super soaker water gun, but a lot of the dart guns, Nerf dart guns, are actually based on my patents. Most people don't know that. How did super soaker get launched, and how did I get the relationship with Hasbro? Well, let's see. I got the idea for super soaker in 1982, so it's been around a while. It wasn't until 1989, though, that I met some people at a company called Laramie. During those years in between, I had built several guns, had been talking to several companies, having one setback and one disappointment after another, but through all of that, kept pushing, did not give up. I persevered. By '89, I went to New York and I was walking the hall at a trade show, a toy trade show. And I was just talking to people who were there with various toy companies, and met some people at Laramie. And told the people, say, look, I got this toy idea. They said, fine, but we can't talk to you now. We're at the trade show. We're talking to people who buy companies to the stores, to Walmart, Toys R Us, Kmart and those folk, and we're setting up deals. I can't talk to inventors here. But our headquarters is in Philadelphia. If you're ever in the area, drop in. Would be glad to talk to you then. I said, fine. And then on my way out, he says, well, don't make a special trip. It was like, don't call us, we'll call you kind of deal. Well, I left. I was in California at the time, living in Pasadena, working at JPL, and got home. It took me about 2 weeks to build my final generation of the water gun, which was the one that had the bottle on top. This was the first time I put the bottle on top. And as soon as I got it finished, I called the guy up at Laramie headquarters. He was the vice president there, and told him, I'm going to be in your area next week. Are you available? And met with him and the president of the company, and demonstrated the gun. They went, wow. They got very excited about it, and the rest is history.
So based on that, him doing presentations here, every summer for the last 5 summers, the students go over and see the research that they're doing at Acceleratron. And in fact, that's one of their most exciting site visits, because here's an African American who not only has been successful financially, but has been an unprecedented, African American inventing things that could potentially change society.
We're going to test our prototype batteries, which are lithium-air batteries, for low pressure and varying temperature. We essentially want to recreate some of the conditions the battery will face in the upper atmosphere. So it would be a cooler environment, a low pressure environment. So we tested voltage of the batteries in colder environment and under low pressure. What kind of electrical power we can provide to the rest of the platform. And then if that's not sufficient, then another group can plan accordingly. And at the maximum, which is hopefully 100,000 feet, it'll be very low temperature. Place the battery within a vacuum chamber and run electrical leads out of that chamber and monitor the voltage as the pressure drops. Every 5 minutes, we'll increase it up. We're gonna raise it up. So our pressure is now at 10, all right? Inches mercury.
I'm Becky Tom McKinnon. I am from the battery science team. We are experimenting the battery to see how it performs in the conditions of low pressure. And as of right now, we are testing the battery in increments of 5. Every 5 minutes, we increase or decrease the amount of pressure that's contained in the vacuum chamber to see if the voltage changes or fluctuates at all.
Still at 2.84. Yeah, go ahead to 15. For atmosphere. So we are attempting to test the battery in the laboratory. So to that effect, we'll test pressure or negative pressure using a vacuum chamber, and we will test low temperature conditions using a refrigeration. Well, essentially what we want is a stable battery, which puts out a constant amount of voltage. So what we found is there's an initial drop in voltage, but from there, despite colder conditions or low pressure conditions, the battery will continue to put out a constant power output.
The robotics lab is really a hands-on lab. I mean, I give instructions at the beginning on what the robotics is all about and how to use the robots, but they go through all the tutorials and they themselves come up with a design the implementation and the testing of the robots.
The LEGO Mindstorm series of kits contain hardware and software to create small, customizable, and programmable
I'm
robots.
from robotics, and I'm demonstrating our project right now. The main idea of this project is to open a few different valves for graphene and biomaterials, if we may, at different atmospheric pressures. Okay, this right here is what's called the NXT, or the brick. In layman terms, this is the computer for the robot. We upload a program from our laptops or desktop computers into the hard drive of this. We hit a button, and based upon what program we've selected is how it's going to work.
This team was given the specifications needed by the sustainability and graphene teams.
Basically what we do is we test the robot after it's been built by the building team and programmed by the programming team, and we test its function to see if it does everything accurately. If not, we make a change log and tell the programming group what they need to do to change it to make it better.
When we attach the atmospheric pressure sensor, it will read a different temperature, and then it will dictate when the robot moves and screws the capsule and puts it back on. So this design is a lot simpler. It's not as heavy, though it was difficult to build, I think it'll be a better fit for what we needed to do. This is around almost 4 pounds at this point. This has been a very fun experience, and I can't wait to continue it.
Hi everybody, my name is Duminder Samarakon, PhD candidate in Clark Atlanta University. I'm one of the TA for graphene team, Research Tech. So here my team gonna present our objectives and what we'll be doing in next few weeks. Our main objective is to design a chemical sensor to detect atmospheric chemicals using graphene as a sample.
Good afternoon, welcome to the laboratory. I'm William Slater. I'm working with the graphene team on the Harp project. Now first I'd like to talk about what graphene is. Graphene is a thick sheet of bonded carbon atoms that is often derived from graphite, hence the name. Graphene is a metallic yet somehow two-dimensional structure that is flexible and invisible to the naked eye, elastic, scalable, corrosion-resistant, electrically conductive, thermally conductive, and plasmonic. Its electrical properties carry electrons as swiftly as 1/100th the speed of light, and its temperature conductivity is 12 times that of copper. Graphene has a number of applications. It could be used in medicine for bandages. It can even be used in tattoo making. To continue on this point, my group is going to use graphene to make a sensor, and to elaborate on that point, I will introduce my colleague.
We are the graphene team, and during this experiment, we will be figuring out what chemicals will be attached to graphene in the ground level as well as in the atmosphere. So, in this experiment, we'll be using the substrate, like you already stated, silicon dioxide. With this substrate, we'll be add drops of the graphene mixed with water as well as ethanol, thank you. And we'll be using the pipette, and as we add drops to the silicon dioxide, we have to let it dry. By letting it dry, we will then be able to measure the graphene with the FDIR as well as the Raman spectroscope to measure what chemicals in the ground and atmosphere that will be attached to the graphene.
I've been with termites now for the past 7 to 8 years. That's the long answer. The short answer is that it's so little known about termites. That's what intrigues me. With the other social insects, we know quite a bit about, ants and bees. But termites, still very little is known. And most psychologists study human behavior, but there are several psychologists that study other organisms' behavior. And I just study insect behavior. First day of class, I say, and I tell my lab assistants when they first come to the laboratory, I say, close your eyes. Okay, visualize the word laboratory. Visualize the word laboratory.
Visualize the word laboratory.
And then I said, okay, you got the word
now,
laboratory visualized.
What do the first 5 letters
just
of
look
laboratory
at the first 5 letters. What does it spell?
What word do you see?
And then it hits, it spells
label.
Label.
You open up your eyes.
We're looking at how termites convert cellulose, which is in wood, to a sugar, and the sugar can be used for ethanol. And ethanol is used with gasoline, you know. Then we go to a place called the Atlanta Outdoor Activities Center, which is 2 miles away from Morehouse's campus, and it's a forest within the city. And it was really designed to expose especially children, but also adults, to the forest who live in an urban setting. So we have a good relationship with them. I've had a good relationship with them for a long time, so they let us set traps out there because it's a forest. I've been associated with the Atlanta Outdoor Activity Center, OAC, for probably about 20 years, 25 years. In fact, I was on the board at one time. This is a great place for teaching, but also I use it to catch termites. We set up traps here so that we can get termites for our research. Now, why did I take students out there? I think it's good for students, you know, rather than come in the lab and they see these termites, for them to actually go and see the termites in their natural environment.
My name is Judea Levitt. I'm with Race to the Top group, which is a rising senior group for Clayton County Public Schools. Right now we're looking for termites, and unfortunately I haven't found none.
My name is Derek Witherspoon. For the end of the day,
Yeah?
I'm gonna find some termites.
Hey, hold it right there. Let me see.
a good amount.
We don't have that's the last bucket. This?
Found by Derek.
Found by
You
5.
just gotta dig a little bit.
It's not what?
No, it's not a lot.
It was. They were. They just ran away.
One. Maybe y'all have to dig deeper. They went down, huh?
My name is Derek A. Witherspoon, the
Which
first,
one
not the
was
last.
this one, right?
And there are some termites right here. I don't know what happened. They're getting smarter. They're evolving. I keep trying to tell everybody, but they're not listening.
We can't take any
they're here.
more.
It's good to get out of the laboratory and to be out in the sun. Now, sometimes it's hot and you got to fight up, especially with outdoor activity center. We had to put on bug spray. And,
Well, they like to be in moist
snakes
places,
there.
under rocks and logs. Let's see, this is...
and spiders and other kind of stuff, which the students, some of them freak out when they first go there. Even though they're not afraid of insects, but to go into the woods where it's not sterile like a laboratory freaks them out, but they all tend to enjoy it.
Okay, let's move on.
In an article published in the American Society for Engineering Education's annual conference and exposition, the authors demonstrated that hands-on experience with the balloon launch process improves student scientific learning, motivation, and thinking skills. We have modified this curriculum and created a comprehensive experience suitable for freshman science majors.
What you do is you lift logs up carefully because subterranean termites live deep in the ground, but they come up to the wood and eat in the wood and then go back down. So that's how they, you know.
We want to roll this back, but where's the trap at?
Right here.
I put it. Right here? Okay.
Point at it, right about here.
Okay, so we need to put the log over it, but then put the flag on the other side.
Okay.
Chuck Taylor's.
Oh, he keeps doing that. Not again.
You know, for me, gym shoes, I know how young people are, but I told them we were going out in the forest. So I thought they, you know, most of them have more than one pair of gym shoes. I thought they wear their raggedy, but young people don't have raggedy shoes. They all clean. So. And they lifted it up and somebody said, termites, termites. And
we need a net. We got some termites.
A lot of them.
A lot of them. Okay, right. And try to break it.
Right,
put on somebody back.
Man, who gonna hold the bottle? Right, get that, get that. Right. This, yeah. Pick that up and put it in. Right.
Let's go.
Are these termites? Are you sure?
Yeah, they look like termites.
Wait a minute, let me look at
it.
Wait a minute.
Maggots.
I was about to say, they don't
This ain't nothing but roaches.
I got so happy too.
went and looked, I said, those are ants.
Those are ants. Those are things like maggots or larvae. You have disappointed me for the last time.
It's John Alexander, and I thought I just found termites, but it turns out it wasn't termites. It was more larvae and maggots, unfortunately. They look really similar, but they are different.
He might have been hallucinating.
All they saw was these white things moving around, but if they had looked close, they would have saw an ant under it moving. And I said, those are ants. And they said, ants? And I said, look at it closely. And what's really cool about this Harp is the students learn how to work as a team, but then they got to learn how to work with other teams. I can remember where one of the issues we're going to have is keeping the termites alive when they're going up in space, and one is to keep them warm. And the team that's supposed to be dealing with that said they couldn't be done. And I told my students, I said, it's got to be done. So when the team came back in, I sat back and just watched, and they said, look, this got to be done. You got to figure it out. We'll give you some suggestions, but you figure it out. And I thought that was really cool.
So essentially the termite team needed two things. They need lighting to actually record the behavior of the termites during the experiment, and they also need to be heated to continue their natural behavior. So we were able to provide the lighting aspect, but currently we don't have enough voltage to provide the heating element for the termites. So hopefully another solution will be found with that.
My name is Chandler Brown, and I'm with the termite crew. Today I'm going to be talking with Jalen. He's with the design team. We had a few issues that we needed to express. Three issues in particular. One issue is the major issue of temperature. If the termites aren't kept at the right temperature, our whole experiment won't work, because if it's too cold, they won't move. If it's really, really, really cold, they'll die. And there's no way we can track their movement or anything if they're dead. So you remember how there was an issue with temperature? Yep. So we talked about it and everything, and that is a major issue that we need to be fixed. That it has to be fixed. So a suggestion is a heating element, like a pad or something, heating pad. It could go either on the bottom.
Type of atmosphere though.
No, they have to be warm enough to function, because if they're too cold, they won't move. If it's really too cold, they'll die. So that'll cancel out our whole entire experiment. They can move comfortably at temperatures of 50 degrees Fahrenheit.
But if they don't figure out a way how to heat this, the whole termite experiment is just a wash.
Design changes occur all the time, because what you got initially gets changed. In this particular case we had with the termites, we did not realize we might have to heat them. We felt like we could just insulate them. But that brought another restriction. If we insulate them and then we are trying to video them, we have to have light in our enclosure. So we need to come up with a way of getting light in. And so we went to the battery technology team that has a battery that it's experimental, but it could be used to provide the lighting load that we need. And so we tried to work with them to get them to power some LEDs that would allow our video camera to work inside an insulated enclosure. So ask them to try that. That's the heating element that we need to go underneath our termites.
Hello, I'm William Dula. I'm with the Design, Recovery, and Launch team, and I'm the liaison to the Sustainable Energy team. Today we are testing out our new heating method for the termite group. So I came to Sustainable Energy to hook it up to their solar cells and see what temperature it would get to and how long it would take to get there.
The pre-freshmen were divided into 8 different research teams. 5 teams conducted original research projects, and 3 teams worked on support and development projects to send the 5 original research projects to the edge of space and back.
Good.
Yeah.
This is the number 2 and current is 9.7.
7 milliamperes.
Yeah.
Third one. We did 1 and 2. This one we did.
From the perspective of being over the entire pre-freshman bridge summer science program, I have a unique advantage of talking to faculty and getting their feedback in terms of what's happening.
What I get from working with the students is just an experience that is priceless. It allows me to mentor students. It allows the students to come into my lab and get a first-time experience of actually learning how to do research at a college. And it also allows them to just expand their knowledge and learn new techniques in different areas and see what's available to them.
To get young people turned on to science, and especially African Americans, because we're underrepresented, that gives me some self-satisfaction. It's a good thing.
What I get from the students is seeing students learn, seeing students challenged with a project and rising to the occasion to do that. I've enjoyed many years of working at Morehouse with the Upward Bound program. And while these were high school students, I got to see students who were interested in learning, interested in science, and I enjoy teaching kids how science works.
And it's rather interesting because when I approached the ones that are working with us now and said, we're going to send something to the edge of space and come back. And I showed them some pictures of the curvature of the Earth with the black sky and everything. They got excited. They were like, wow, you mean we're going to launch, we can send something, our research up like that? So they actually came in with a zeal for it. And when the faculty has a zeal for it, needless to say, the students are going to feel that passion. The students are going to feel that energy, which is beyond what a faculty would normally have just in teaching. So why are we going to Wyoming? Last year we went to the Mojave Desert. Basically speaking, we try to find locations that when the balloon goes up, it comes back down. It doesn't come down in a populated area, if you will.
I'm a little concerned about that because the jet stream is different in one area to another area. Right now, the jet stream is not the problem in Wyoming, it's surface winds. And the surface winds are such that it would produce a very prolonged launch flight if we were to launch at this particular point, like today. So we're kind of concerned. We want to go to 100,000 feet, but if the balloon gets pushed several hundred miles away, we may end up in the mountains of Colorado and can't recover the balloon.
The next reason why for Wyoming is we look for partners that can help defray the cost, because we're sending quite a number of people across the country to launch a balloon with all the shipment and everything else. So the University of Wyoming has the oldest, if I'm not mistaken, and one of the largest weather balloon research stations in the nation.
They launch much larger balloons than we launch to study the atmosphere on a regular basis. And so we'll get a tour of their facility. So this is a great opportunity for the students.
Perfect match. They also have an extremely active sustainable energy research group, and this one of our subtopics or issues that we want the students to be exposed to is sustainable energy. So they're touring the research facilities when they get out there, the sustainable energy research facilities, the atmospheric science research facilities, such that they now have a complete picture, not just them launching the balloon, but what other scientists really do. Some of the balloons they launch are 3 or 4 stories high, large, huge balloons. And hopefully the students will get an opportunity to see some of the kinds of things that they do. It rounds the whole picture out. And I really want to thank the University of Wyoming because they're picking up a lot of the costs for housing, et cetera. Because science is not like, well, you're going to do this, 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 and you're going to get these results, and you're going to publish this. Science is like, you got to try it. If it works, great, you can publish. If it doesn't, you got to retool and do it again.
But I'm excited about launching the balloon. I was really excited.
I just don't want the termites to explode, when they come down. Then we won't have any data. We'll just have mesh on the camera.
So my prediction is they're going to have a great opportunity to experience how science works. Whether the wind conditions are just right, or whether the atmosphere or the jet stream takes it 100 miles away, or whether it comes right back down where they predict, we'll see. But what I will predict is that they will have an exciting time in learning how science works.
My name is Don Roth, R-O-T-H, and I'm the Deputy Director for the School of Energy Resources at the University of Wyoming. And I'm also representing the Strategic Diversity Initiation Initiatives Committee that is a central part of the university's effort to improve diversity in relations with other institutions in the United States. This program developed as a result of some mutual relations that we were establishing with Morehouse College, and it was a great opportunity to make connections and allow the Morehouse group to come to the University of Wyoming to be a part of this balloon launch. Our atmospheric science department is very committed and very involved in various balloon launches, and so it seemed like an excellent opportunity for Morehouse and University of Wyoming to collaborate together. Then the group will go to the University of Wyoming. We'll give certain overviews of the university, opportunities for graduate education, specialization programs such as atmospheric science, a lot of the STEM disciplines, the energy resources focus that we have at the University of Wyoming, and we'll be able to discuss some mutual exchange options and possibilities and so forth, and the students will learn about the different degrees and opportunities at the University of Wyoming.
During the first 2 weeks of the summer science program, the robotics team learned how to build and program robots. This team was given the specifications needed by biomaterials and graphene teams. The end result was an original, highly innovative robotic device.
My name is Steve Alford, and I'm from the robotics group. This is the robot that we designed, and this is the final product. The idea of the robot is this right here is for biomaterials for their lab. The idea is once it reaches certain feet, this will open for them, so they can their materials can react in the atmosphere.
Constraints are 6 pounds per payload, and this withstood the 6 pounds. This is 5.77 pounds actually. And with the camera is going to view both the arms, unscrewing the caps. And basically what it's doing is these materials are going to react in the atmosphere, and we're trying to record what it does.
This seemingly daunting
so that's the purpose of the
engineering task
graphene
for
and the
undergraduate
biomaterials.
pre-freshman students was easily accomplished with the Lego Mindstorm robotic
we're
kit.
running in through the building. The hose is we're gonna connect it up to the neck of the balloon and inflate the balloon with helium.
Yeah, this is all tied off with tie wraps and tape. So, we got plenty of hoses.
The robotics team worked with the launch and recovery team to construct and program a robot that would open and close vials containing the research materials.
Computer screen, it'll actually show a map with where the balloon is.
Hello, I'm William Dula. I'm from St. Louis, Missouri, and I'm on the design, launch, and recovery team. Today, we are going to set up the Harp. We're going to launch it, and then later, while everyone else is touring the University of Wyoming, the design, launch, and recovery team is going to go out and find it.
We need to check all of them because in the handle we're mentioning about this is actually tied to the LED here. To be done by students. I'm there to help give them assist if they need it, but I'd rather have the students do the whole thing. Fill the balloon with helium, release the balloon, track it as it flies, recover it. I'll just go along and enjoy the walk, but I want the students to do the recovery.
My name is Davis Turner, and I'm representing Morehouse College and the HBCU pre-freshman program. This right here is the Harp platform, and we'll be launching into the stratosphere in a few moments here. And while it's in the stratosphere, we will be conducting several experiments. One being a lithium-air battery, second being biomaterials, third being graphene, fourth being termites. And it took a lot of ingenuity and creativity, but we're finally here, and I'm really excited. And then when the balloon is released, it all goes up in one nice fashion. More, come on, a little more. Everybody get in line with Steve. That looks good right there, Steve. One, two, three. Wait, we're not even... Whoa! Hey, hey, hey! You had the robot on.
Once it goes down on the ground, the telemetry usually cannot reach over 2 or 3 miles away from where that impact site is. So you need to be close with your recovery team so that when it comes down, they know where it's coming down and can get close enough to get a signal from that.
Robots.
Once you get there, usually you can't drive into where you need to pick it up, so then you have to use a handheld GPS system. And you take the coordinates from your last read from the unit as it was going down, where you think it is, and then you try to hike in and find it. Did you do the conversion? Okay. Because they were in the wrong units.
As far as fee goes?
No, in terms of, so you have to have degrees and you have to have minutes. And he's got decimal.
Will. Will.
The satellite beacon acts in a different manner. It, because it uses a satellite, can broadcast up to the satellite if you can see it, and then give you a location. But that's not usually readily available in the field. It's a backup in case you can't find it with the primary system.
Are we close?
I think we are, but I'm not sure. We lost the signal on the antenna, and so
All right.
It's reading again, guys.
And it's
okay.
on the west side of the road, it looks like. Yes.
Okay. So we're getting a signal again?
Yes.
Okay, good.
Good deal.
41.39984. And then negative 105.17802.
I can also start up. I've got my computer, our department laptop here. And
Okay.
I have a GPS puck GPS with a street atlas. So we could start that up too.
Okay.
Okay, and that'll give us our location exactly. That way, if you lose
The Stratostar high-altitude balloon kit used in this HARP experience creates the foundation for the adrenaline-charged Edge of Space learning experience. This kit contains the high-altitude balloon, a software program that allows students to predict where the balloon's payload will land, a GPS tracking system that allows students to track the balloon in real time and recover its payload as it lands, video cameras that record the flight, as well as a series of other instrumentation that records altitude, atmospheric pressure, humidity, and temperature.
We also have another issue that occurs in our balloon launch. There's no backup of the data that's collected from the research projects on board, so it broadcasts that information down to our computer system that has an antenna on the vehicle, and as it travels, it collects not only the GPS data, it's also collecting the research data.
Data through satellite, GPS, and this is our backup, the beacon module.
And we'll connect that in and we'll get this figured out.
After the balloon is sent up and after they recover the data, then they have 2 weeks now to go and analyze the data that they received, as well as to develop PowerPoint presentations and poster presentations that they will present at the end of the program conference, where we'll invite the president of Morehouse and we'll invite faculty and staff and other students that may be interested, such that they may present their scientists as scientists do at scientific conferences and get that opportunity to see the completion of a whole project.
Our solar cell was safely landed, and we got the data. So these days we are analyzing the data. We are lucky.
Well, the results from Wyoming was a little disheartening because we lost the robot.
It was unfortunate that the robot was lost with our actual biomaterials. So at this point, it's inconclusive on what the after portion of our research would be. However, it shows the students that this is a learning experience, that this is science and things happen, and it's not just a cookie cutter type of lab where if you do this, you're going to get this result.
The HARP project continues in the fall from the perspective that in February, the National Science Foundation, along with the AAAS, the American Association for the Advancement of Science, has an undergraduate conference for minority students that present their research. So it will continue in that the students that get good results and that do a good job this summer, we will travel them. Usually the conference is in Washington, D.C. We'll travel them to Washington and they'll present their data at that point. Outside of that, the next project will be next summer, where students from that come in the next year will pick up where these students left over. There's memory from what they did before, from the PowerPoints and from the posters.
Students should take advantage of this program because it allows them to get firsthand exposure to actually doing experiments. So it's a really good experience for students just to come in, get new exposure to the environment at Morehouse College, work with professors, work with other students, and just being able to come back and present their research at the end of the summer.
Meeting science majors in their freshman year, forming strong relationships.
If you can give a student an opportunity to see that I really love this, the probability of them being successful is much, much greater. And basically speaking, our whole objective of this pre-freshman bridge summer science program is to bridge them into college, allow them to have a successful college matriculation, and then go on to get a PhD and become real scientists.
This is an individual or a student who's really interested in going ahead in science. This offers him an opportunity to really get involved instead of waiting until possibly a graduate program.
If for nothing else, it teaches them teamwork and it teaches them leadership.
We've done research in the past to show that these are outcomes that we actually see. One, the students get a real understanding of how science really works and the nature of science. Two, they get an understanding of the interdisciplinary nature of science because you've got to have a design and launch recovery team. You've got to have a robotics team to create the devices to open and close the experiments for the graphing team or the other teams. So they understand how to work together in a large research project or the interdisciplinary nature of science, just as if you were sending up a space shuttle with different individuals with different missions. Well, some of the improvements that we've been seeing year by year in our pre-freshman bridge summer science program has come from assessment one of what we're doing and then shifting and altering the program as we go along. So it's a gradual process of us studying the students. We give them lots of assessments. We have an externally evaluated, we pay quite heavily to be able to let us know what we're doing. And as we see things that work, we incorporate it or make it better, and we see things that don't work, we drop it out.
I knew doctors and dentists and teachers and principals and preachers, detectives. I didn't know any black scientists, none. When I was growing up, I knew I wanted to be a scientist.
I really want to thank Clark Atlanta University TV for being partners in this process because you have really done an excellent job in bringing everything together and calling this project your own as well. With the kinds of opportunities that television stations are giving for STEM programs, especially STEM programs that are bridging students in, what this will do is stop the paradigm thinking that when you see a group of black men walking together on a college campus, there goes the basketball team. There goes the scientist, there goes the chemist, there goes the scholarly achieving students. And what CAU is doing in programs like this is creating the image that African American people should have always had.
My name is Darkea Reuben.
Dr. Juana Mendenhall.
Science is cool.
Science has swag.
They call me Kurg, and science is cool.
An original flight conducted by the students, the payload with the cameras that took pictures was lost. However, the students built another payload and program. Staff subsequently launched this payload and recorded pictures.